So hi everyone, welcome to my channel again. Today in this video we are going to explain the topic variation of pressure in fluids. Now basically if you have a vessel containing some fluid, okay. Now if I consider 2 points, so this is point 1 and this is point 2. Now these 2 points are within the fluid. Now pressure, how do you define pressure? Pressure, it is defined as force experienced per unit area. Force experienced per unit area. Now at this point, the force at this particular point is due to the weight of the fluid above this point. Similarly, force at point 1 is due to the weight of the liquid or the fluid above this point 1. So obviously force at this point will be greater than force at this point. Now if force is greater, pressure is obviously greater. So this implies pressure at point 1 is greater than pressure at point 2. So this is our common observation. Okay. Now suppose in this fluid, between these 2 points we consider a cubical volume. We consider a cubical volume. Okay, so let's enlarge this cubical volume. Okay, so now basically this is a cube within this liquid. Now let's say rho is the density of the liquid. So rho is the density. Okay, now say A is the area. A is the area of each face. Okay, now we know that fluid pressure is always normal to the surface in contact. Now let's say pressure on the lower surface, it is P. It is acting in the upward direction. Similarly, on this upper surface, the pressure is acting in the downward direction and it is say P plus dP. Okay, don't worry about this plus sign. I don't yet know whether this sign is positive or negative. If this sign is positive, pressure will increase in this direction. If this sign is negative, pressure will decrease in this direction. Okay, now suppose these two surfaces are separated by height y. So this height is y. Okay, or say dy. Let's say a small height dy. Okay, now the weight of this part, it will act in the downward direction. Okay, weight is acting in the downward direction. So this cubical volume, it is acted upon by 3 forces. Force due to this pressure acting in the upward direction, force due to this pressure acting in the downward direction, and weight W acting in the downward direction. Now if I apply equilibrium condition, so equilibrium condition, what it says, translational equilibrium, net force has to be 0 or total upward force equal to total downward force. Remember, A is the area, P is the pressure, okay, on the lower surface. Now pressure is force by area, so force is pressure into area, so total upward force is P into A. So this is the total upward force. Total downward force is this pressure times area, P plus dP into A, and weight, it is also acting in the downward direction. Okay, now this weight W is mg. Okay, now what is this mass? Mass is volume into density. Volume is area into length of the side. So this is A dy. Okay, this is volume into density. So that is mass. So that means W is equal to A dy rho g. So if I substitute this value over here, what do you get? We have P A is equal to P plus dP into A plus this quantity A dy rho g. So this all A cancels out. This PP also cancels out. So finally we are left with dP is equal to minus rho g dy. Okay, so that is, see, if height is measured from the bottommost part, okay, so if height is measured from this part, so as you move, so this is, if this is x-axis and this is your y-axis, so if you move along this part, the value of y increases. Okay, so when you move between the two surfaces, the value of y increases by dy. So this expression shows that when height increases by dy, that is when you move from the lower surface to upper surface through a distance dy, the pressure decreases. Why? Because there is a minus sign, and this is the decrease in pressure when moving through a vertical distance dy. Okay, so this negative sign, it shows that as y increases, P decreases. Okay, so now mathematically we are sure that as we move from 1 to 2, the pressure decreases. The pressure decreases. Okay, now let us see how much is the decrease in pressure. Okay, so for the same liquid, for those 2 points 1 and 2, so this point 1, this point 2. Okay, so this pressure at point 1 is P1, pressure at point 2 is P2. Now these two are separated by, say, vertical displacement, or say let it be h. H is the, it's not dy now, it is h. Okay, so now let's say that this height is y1 for point 1, and for point 2 it is y2. Okay, so pressure at this point is 1, pressure at point 2 is 2, this is P2, this is P1, the 2 points are separated by vertical height h. So this is from, height is measured from this end, so this is y1 and this is y2. So that means y2 minus y1 is equal to h. Okay, so now we have this expression for dP. We have dP is equal to minus rho g dy. Now let us integrate this from y1 to y2. This is P1 to P2. So if you integrate it, what do you get? We get P2 minus P1 is equal to minus rho g y2 minus y1. What y2 minus y1 is h, so we have P2 minus P1 is equal to minus rho g h, or P1 is equal to P2 plus rho g h. That is, the pressure difference between these 2 points is equal to rho g h, and P1 is greater than P2. P1 is greater than P2 by an amount rho g h. Now let us see what happens if the vessel is not at rest. Previously, the pressure difference was calculated for vessels at rest. The fluid was at rest, the vessel was at rest. Now let us consider a case when the vessel is accelerating. So we will be basically considering 2 cases. First case, vessel accelerating along x-axis. Second case, vessel accelerating along y-axis. X-axis and y-axis. So first let's say what happens when the vessel accelerates along x-axis. Now if this is the vessel, okay, and contains some liquid. Now this vessel is at rest. Now if this vessel starts accelerating in this direction, say ax is the acceleration along x-axis. So we have taken this direction as x-axis and this direction as y-axis. Okay, so if the vessel initially is at rest, so level of the liquid will be like this. The moment it starts accelerating, the liquid level will change to this. Okay, the level of liquid in this part will rise, the level of liquid in this part will decrease. Okay, so now this is the level of the liquid, this is the way the liquid will behave, the top surface of the liquid, if the vessel starts accelerating in this direction with acceleration ax. Okay, now let us consider a cylindrical volume inside the liquid. Okay, now let's say this height is h1 and this height is h2. This height is h1, this height is h2. This cylinder is of length dx. Dx is the length. Okay, now this system, it is accelerating in this direction. So if the system is accelerating in this direction, let's apply Newton's law of motion. Suppose pressure on this part, it is P, pressure on this part, it is P plus dP. P plus dP. Cross-sectional area is A. Cross-sectional area is A. Okay, so now see, on this surface the force is acting in this direction. On this surface the force is acting in this direction, but the entire system is accelerating in this direction. So that means the net force acting in this direction is greater than the net force acting in this direction. So what is the effective force? Let me redraw this again. For the cylinder, this side force is P into A. This side the force is P plus dP into A. But effectively this system is moving in this direction with acceleration ax. That means net force is equal to, net force, how much is the net force? PA, okay, force on this part, minus P plus dP into A, force in this direction, is equal to mass into acceleration. Mass of this part, m into ax. Okay, so that is PA minus P plus dP into A is equal to mass. Mass is volume into density. Volume is area into length of this cylinder is dx. So dx, so this is a volume into density rho into ax. So this AA cancels out, PP cancels out. So what are we left with? Minus dP is equal to minus rho ax dx. Okay, so that is dP by dx is equal to minus rho ax. So this is the gradient, pressure gradient dP by dx. So dP is the change in pressure when you move through a distance, dx. So this is the decrease in pressure when you move through a distance, dx, for a liquid vessel which is accelerating in horizontal direction. Okay, now let's say what happens if the vessel starts accelerating in the vertical direction, vertically upward direction. So this is a vessel containing some liquid. Now again let us consider a cylindrical volume. Okay, let's say height is dy. This is x-axis, this is y-axis. The system is accelerating in the upward direction with acceleration ay. Okay, so pressure on this part is P plus dP, pressure on this part is P. Again let's say A is the cross-sectional area. A is the cross-sectional area. Now system is moving in the upward direction. Okay, so if system is moving in the upward direction, that means the net force is in the upward direction, and net force is equal to mass into acceleration. So this is the net force, okay, or effective force. So net force is in the upward direction. So this P pressure it is acting in the upward direction. So force acting in the upward direction is on the surface, it is P into A. This is the total force acting in the upward direction minus total force acting in the downward direction is the weight of this part, weight of this cylinder, plus force due to this pressure, P plus dP. So that is P plus dP into A minus A into dy, cross-sectional area into length of the cylinder. This is the volume into rho density into G. That is, this is mg, weight of this cylinder acting in the downward direction, is equal to the net force. Net force, mass into acceleration. Mass of this cylinder is A dy, this volume into density into, this is mass into ay. So that is the acceleration of the system. Okay, so again this A cancels out, PP cancels out. Now if you simplify this, you will have dP by dy is equal to minus rho G plus ay. So this is the pressure gradient if the system starts accelerating upward, okay, with acceleration ay. Now from this expression you might have guessed that if this is for system accelerating upward, for system accelerating downward with acceleration ay, it will be dP by dy is equal to minus rho G minus ay. This plus ay will be replaced by minus ay. Now let us see one more case. Suppose this vessel containing the liquid, it is accelerating in this direction with acceleration a. A is the acceleration, okay, and this is the top surface of the fluid. So as I told you, the liquid, this vessel accelerates down in this direction, the liquid will move in the, because of inertia, this at the back surface on the backward part of the vessel, the liquid level will rise, in this part it will fall. The liquid will move in this direction because of because of inertia. Okay, so let us calculate the inclination of this free surface. Okay, now see, if we consider a cylindrical volume inside the liquid as done in the previous part, this is say H1 and this is H2. Okay, these two parts are separated by distance dx. So if the system is accelerating in this direction with acceleration a, we have already obtained dP by dx as minus rho a. So that gives dP is equal to minus rho a dx, minus rho a dx. Now that means, see, if say this part pressure is PA, this part pressure is PA, and this part pressure is PB. Okay, and this total separation is x between P, this surface, and this surface. The separation dx is replaced by x. So in that case, if I integrate this from PA to PB, the 0 to x. So what do we have? We obtained PB minus PA is equal to minus rho a x, or I can write PA minus P minus PB equal to rho a x. Okay, acha. Now one more thing, from this diagram, this is at height h1, this is at height h2. So if atmospheric pressure is P naught, if atmospheric pressure is P naught, so can we write PA is equal to P naught plus rho G H1 and PB is equal to rho naught plus rho G H2. So if you substitute those values in this equation, what do we have? We get rho G H1 minus H2 is equal to rho A X. Okay, so that gives H1 minus H2 by X is equal to, this rho cancels out, is equal to A by G. A by G. Now if you see this cylinder, this is H1, this is H2, this is X. This was assumed to be X. So H1 minus H2 by X. Basically, this quantity gives you this value. Suppose if this angle is theta, so that will give you the slope tan theta. So that is, this equation is tan theta. Okay, so that gives tan theta is equal to A by G. So this is the inclination of the free surface. Inclination of this free surface when the vessel accelerates in this direction with acceleration A. Acceleration A. Now this expression, this inclination of the free surface can also be calculated in one more way. So this is the vessel accelerating in this direction with acceleration A. This is the free surface. Okay. So at this point, this is the weight mg. Okay. As I told you, if the system accelerates in this direction due to inertia, this system is experiencing force in the backward direction. So this is ma, and this is the net force F net. Okay. Now if this angle is theta, this implies this angle is also theta. Okay. Now in this part, if you apply, what is tan theta? Tan theta is equal to perpendicular by base. Perpendicular is ma, that is equal to ma by mg. So this cancels out. So again we are left with tan theta is equal to a by g. So this is another way we can measure the inclination of the free surface. So this is first part of the series for variation of pressure with various cases, depth and acceleration and all. There will be 2 more videos on this particular topic which I'll be uploading very shortly. Thank you for watching this video, and if you have any doubts on the topics discussed in this video, you can post in the comment box. Good luck.